Okay, week after Monday, 19th of June will be the exam date. It will start 11 a.m. and end 1 p.m. You can bring one A4 page with all formulas you like to use, and right, that's it. Last time we discussed about the finite difference method. It can be used for any kind of differential equation, and we are going to use FDM for the waveguide equation. And as I mentioned earlier, waveguide equation is exactly same as the Schrödinger equation for by using a scalar wave approximation. And we'll cover how we can derive the scalar wave equation with the PowerPoint file uploaded today, the waveguide. So we'll cover this later. And there is a homework number 8, and it's a finite scale potential problem, one-dimensional problem, and you can use the method we have introduced to solve this equation by just a few lines of modification. Is there any question about the problem number 8? Okay, and we have covered 8.1, and we have covered 8.1, and we'll start covering 8.2. And 8.3 as well. Let's review first the contents we have covered last time. Any question about the content we have covered about the finite difference method? 뭐 너무 쉽죠? Isn't it too easy? It's just the first order Taylor expansion. Right? So the concept is very easy, but the result is quite impressive. So by using just this kind of simple statement, and the only statement actually used is the eigen command, which finds the eigenvalues and eigenvectors for the n by n matrix A, and everything else is just to define what is A, right? And the psi and E, psi is the eigenvectors as a column vectors of the n by n matrix given by the MATLAB, and E is the diagonal component of E. E is also n by n matrix, and diagonal components of E correspond to the eigenvalues for the eigenvectors given as psi. Right? So only thing you have to do is find a physically meaningful eigenvalues and eigenvectors, and for a given eigenvalue, you can just plot it, because plot it by using the psi, and psi are the, what are psi? For a given eigen value E, for a given problem, this is a X, and homework is like how to solve a potential given like this up to 0. Is that 3 or 2? I think 3, right? Minus 3. Potential is, this is 9 and 9, and the potential is constant after when x is, absolute value of x is greater than 3. Right, so let's assume that there is a eigenvalue, 2 eigenvalues, E1. If we start sampling the solution psi from psi x from x is equal to minus 5 to 5, for example. Sorry, I should, because there is a one student who is doing, who cannot attend this course, so I'm taking a video tape for this. So if we'd like to define psi from minus 5 to 5 with the number of data points n as 201, then we sample the solution of psi with the equally spaced sample data point. So if so this program will provide 201 eigenvalues and 201 eigenvectors corresponding to that eigenvalues. So for example, E26 is 4.2, and E121 is 8.1, and rest of them are larger than 9. Then there are only 2 solutions which are physically meaningful for this problem. So for a given eigenvalue, 26 eigenvalue, then psi is given as 201 by 201 matrix, and this is 26 eigenvalue, so we should take 26 eigenvector, and these are the psi 26, right? And these values, let's say this is A1 to A201, then these numbers correspond to the psi 26 as a function of x, but it is sampled with the equally spaced data point. So sampling space over here is 10 divided by 200. Right? So h is, sampling interval h is given as 10. 10 is from minus 5 to 5, right? So interval is 10, and we took 201 data points, so the interval is 200, 10 divided by 200. So these are just solutions. The only thing you have to do is find this physically meaningful eigenvalue, and then we just took this one eigenvector and plot this one, and that's the solution. So those are the flow chart of a simple MATLAB program by using the FDM to solve a Schrödinger equation. Right? So it's a very simple and straightforward method to solve a one-dimensional Schrödinger equation. Right. Only thing you have to do is, what is a reasonably good interval for the x and how many sampling data points we are going to take within them. So these two can be decided by from experience. So if we take as we know that the eigenfunctions corresponding these two eigenvalues should look like this one. So as x goes to infinite, it should go to 0. So for this problem, after if x is less than -5, the data point, the psi, is about 10 to the -4 or 3 compared to about 0.2 or maximum or minimum values. So we can ignore, we can just take the x values, boundary of x from -5 to 5. If you like to increase this to 100, that's okay. But then all the data points up to -4 are effectively 0. So you're just wasting lots of data points. And if you take the interval of this problem from -100 to 100, then if you like just take 201 data points, the sampling interval is just 1. So we have just 1, 2, 3, 4 data points within these values. These 1, 2, 3, 4 data points within this important the range of x parameters. So you need to increase the data point. If you like to take the -100 as the starting point of interval, you should increase the data points from 200 to 20,000 or 2,000 and more. Then the matrix size becomes 2,000 by 2,000, and you'll automatically produce 2,000 eigenvalues and 2,000 eigenvectors. Only 2 out of 2,000 meaningful solution. So you need to decide how many data points you need and what is the range of x parameter for a given problem. So that can be decided by from your experience. So that's the situation we have. As I mentioned, homework is to solve this kind of analytically unknown Schrödinger equation solution. But with MATLAB, you can easily obtain the solution of Schrödinger equation for this kind of arbitrary potential. Right. Let's say, let's go to the other differential equations we can solve with MATLAB is the heat equation, and I'll just explain briefly. This is just a extra content to make you feel comfortable about the finite difference method. Heat equation or the electrostatic equation are the two other problems, popular problems we can solve with the finite difference method. The heat equation is given like this. The temperature of a material at a given point, the time derivative of a temperature let's see, the time derivative of a temperature is given as the divergence of J, and J is the K times the gradient of U. And K is the heat conductivity, and the K is heat conductivity. And the J is K times gradient of U, and the whole equation becomes like this. The time derivative of U becomes minus K del square of U. And for a time-independent equation where there's no change of a temperature for a static problem, then we can take this 0 and we have just a Laplace equation. The Laplace equation is a typical example for a finite difference method. Another example of Laplace equation is the electrostatic potential. Del square, when there is no charge inside, if there is no charge inside of the material, then divergence of E is equal to 0, and as the E is the minus gradient of potential V, then del square potential V x, y, z is equal to 0 for a space without any free charge. Then this is another typical problem. If we have a voltage given at this boundary, and V2 is given at the another boundary, what will be the potential between these area? If we have a metal conductor and another conductor, and this is a semiconductor material between these two metals, and if we apply 5 volt for V1, and if we apply 0 minus 2 volt for the another metal, then what will be the electric field between these two metal plates? That's a typical problem we need to solve. And this is a potential solved by the finite difference method between the two plates, metal plate. This is potential. And if we take the gradient, of minus gradient of this potential, then we can find the electric field between these two plates. So these are typical problems. It can be effectively solved by the finite difference method. This is another example of heat equation. Heat equation, as I mentioned earlier, heat equation is another Laplace equation. And if the temperature at these three boundaries are given as 0 degrees, right? If three boundaries are given, temperature of three boundaries are given as 0 degrees Celsius, if this plate is 120 degrees, what will be the temperature between these within this rectangular material? And if the conductivity of this rectangular material is given, we can calculate temperature between these two spaces. And this is another typical Laplace equation. And we can easily solve this Laplace equation with this. So these are content which is taught in the electrodynamics, graduate school electrodynamics in this semester. And I just introduced this one to explain what are the other purposes of the finite difference method. So the differential equation, the scientific problems we learn in science, College of Science or College of Engineering, is just solve a given differential equation. How many differential equations we learn? Newton's equation. Newton's equation is not solved by the finite difference method. It is just there is a well-known method, Newton's method. It is also Taylor expansion, but that is categorized as the initial value problem. These are typical examples we can solve. If there is two bars connected like this, and string, for example, string without any mass. Let's say this is N1 and N2, and this is L1 and this is L2. And if I initially stop this one by hand, let's say this is theta 0 is 10 degrees, right? And theta 0,1 is 0 degrees, 0,2 is 10 degrees. If I start this one at t equals 0, then what is the period of this oscillation? Can you solve this?
컴퓨터로 가능하지 않나요?
Right, of course you need to solve this with a computer. With your hand you cannot solve it. Right, but if I am a dean of science college, I will not let you graduate if you cannot solve this kind of sim problem. Right? So you should think you are lucky because I'm not a dean of science college of science in this university. So this is a very simple problem, right? You can solve it just Lagrangian. If you define a Lagrangian, then you can solve this by it's called Lange-Kutta method. This is just a two-step Newton's method. Newton's method is just Taylor expansion of time derivative. So you can this is much simpler than the finite difference method, concept of the finite difference method. Anyway, this is an example of a typical example of a differential equation. And this is the Newton's equation. Second one is Laplace equation. The divergence E is equal to 0, and what is the electric field between the two given boundary given by two metals. These are typical examples. Or heat equation. But if the temperature changes, boundaries of temperature of a boundary changes with respect to time, it will be a little bit more complicated, but you can solve it anyway. And the third one is Schrödinger equation. Right? So Schrödinger equation is eigenvalue equation. This is Laplace equation. This is Newton's equation, Laplace equation, and this is Schrödinger equation. And these are eigenvalue equation, and this is boundary value equation, and these are the initial value equation. So these are the three equations we learn in physics department. In engineering department, there are several other, not many, only about few, 5 or 4 or 5, depending on department. There are 3 or 5 differential equations to solve to solve a problem. These are the general contents we learn in science and engineering department. For a given differential equation, how to solve it. You learn this for 4 years, and another 2 years in graduate school. Right. So these are all the content we learn And we already covered this problem, and we just introduced how it works, but it is as simple as the Schrödinger equation. So I'll just explain how we can use the two-dimensional differential equation. These are the explanations. First, I didn't copy right, these are the Taylor expansion. If we have a del square operator, then these are the arithmetic representation of del operator with a sample data point. Right, I think before we explained that before to derive the finite difference method for one-dimensional problem, we use if there is a sample data point along the x-coordinate, right? Then this is the I, and this is I minus 1 sampling point I plus 1. Then these values f x I minus 1, and this is f x I, and this is f x I plus 1. Then the derivative of the del square of f is my first one, round f over round x can be written as the what's that, if we this is f, this is I, we define this as the f I minus f I minus 1 divided with the h. H is the spacing between this, and the derivative of f at I plus 1 is defined as fi plus 1 minus fi divided by h, right? So by combining these two, round x square round fi is just defined as h round f round x I plus 1 minus round x round fi. Right. So by applying these two, we have the h square so this is fi plus 1 plus fi minus 1 minus 2 times fi. Right? So these are the representation of the second order derivative with respect to x-axis by using the sample data point. So these are just the summation of this data point and this value minus twice of the value at the center and divide by the h square, which is the square of the sampling interval. So if we extend this to the two-dimensional case, del square f is just the round x square round square f plus round y square round square f in two-dimensional space in 2D. So we have just represented this, and over at the PowerPoint file we define the sample data point at the center is uij, and along the x-axis one sorry, we define this is x-axis and this is y-axis. Right. This is for simplicity. This is to make this consistent. Over here in the PowerPoint file, the vertical is the x-axis and horizontal is the y-axis. So the horizontal vertical one is the x-axis. So we just write down, instead of f, we use u as the sample data point. Then along the x-axis, that is h square u I plus 1 j plus u I minus 1 j. These are the two sample data points from the neighboring point, and minus twice of the uij. This is the round x square round square u. Right? And the round y square round square u is also can be written as h square u I j plus 1 plus u I j minus 1 minus 2 u I j. So if we add these two, then we obtain these things. If we add these two, then del square of u is h square, and u I plus 1j plus u I minus 1j plus u I j plus 1 plus u I j minus 1. These are the four neighboring points, minus 4 times the sample data point at the center, uij. These are just a representation of del square in the two-dimensional space. Because if there is a matrix M, Mij is the ith component from the top and the jth component from the left. If Mij, then this is how we define a matrix. So first index define how many elements are from the top, and J defines how many elements are from the left. So, to make this consistent, I define x-axis as the first index corresponding to the first derivative, first index, and y-axis is the corresponding axis for the second index of matrix. So that's why it is defined like this.
샘플링 인터벌에 따라서 아이겐밸류나 그런 게 달라지는 일은 없을까요?
달라지지 물론.
그,
여기 우리 프로블럼 호목 해보면
네.
if you have a different sampling data point, then your solution will be a little bit different.
그러면 저희가 얻은 솔루션이 맞는지 아닌지 여러 가지 샘플링 인터벌을 해가지고
그렇지.
겹치는 부분.
그렇지. 그게 컨버징, 샘플링 인터벌을 작게 하면 작게 할수록 좋잖아요. 근데 작게 하면 작게 할수록 데이터 포인트가 많아지니까 매트릭스 사이즈가 커지니까 계산 속도가 느려지죠. 그것만 참. 그러니까 계산 속도가 안 느려지는 한 샘플링 인터벌을 작게 해야죠. 근데 아무리 작게 해도 아까 그 경우에 뭐 0.1이라고 잡았다고 보죠. 홈워크 할 때 H를 0.1로 잡았을 때 솔루션을 구하고 그 다음에 그걸 10배 더 작게 해서 0.01로 했을 때 솔루션을 구하는데 차이가 10의 마이너스 5승밖에 차이가 안 나. 그러면 더 늘릴 필요가 없는 거죠. 그렇게 컨버징을 합니다. 컨버징을. 데이터 포인트를 많이 늘리면 늘릴수록 좋지만 그 컨버징하는 속도가 있잖아요. 그래서 그걸 뭐 데이터 포인트를 100만 매트릭스로 하면 좋죠. 근데 그러면 한 몇 시간 걸리니까. 그리고 웬만한 컴퓨터에서는 아웃 오브 메모리로 에러가 뜨니까 할 수가 없으니까 그걸 줄이기 위해서 이제 그걸 조정을 해야죠. 그리고 인터벌도 아까 5에서 마이너스 5까지잖아요. 근데 그걸 10에서 10 하면 더 좋죠. 더 좋은 솔루션이 나오죠. 그것도 역시 무한대로 늘리면 그것도 컨버징 합니다. 근데 그걸 무한대로 늘릴 수는 없잖아요. 그러니까 컴프로마이즈 해야죠. good point. So there is the smaller the sampling interval or the larger the number of data points produce better result. But if you make sampling point larger or the sampling interval smaller, then it increase the size of matrix A and it will decrease the computation speed. So you need to compromise between the computation speed and the convergence of the solution.
이제 계산할 때는 저희가 지금 XY 엑시스를 나눴으니까 이게 이 다른 방향으로는 고려하지 않고 그냥 딱 엑시스 맞으면 다 풀리는 거인 거죠 이게 지금.
그렇죠.
그럼 만약에 저희가 데이터 계산상으로 따졌을 때 엑시스를 세 개로 그러니까 3디멘전이라고 해야 되나?
그렇죠. 라플라스 이퀘이션 3디멘션을 풀 수 있죠.
왜냐면 이제 저희가 이걸 만약에 코드를 풀 때 이제 그 힐버트 그 스페이스상에서 이제 이 2디멘션을 세 개의 엑시스로 풀게 되면은 그런 경우도 그러면 이제 그만 고려되면 똑같은 경우가 나오면 먼저 한번 해볼 수 있는 거네요, 시도.
그렇죠. 하이드로네이션 프로그램 풀 수 있죠 이거. 아무 저거 없이 그 저기 뭐야 스프리컬 하모닉스 있잖아요. 그거.
예.
그거 아무 고려 없이 그냥 바로 솔루션을 풀 수 있죠. 컴퓨터만 좀 좋으면. 그렇지.
샘플링 포인트를 n개로 잡으면 아이겐밸류가 n개가 나오잖아요.
그렇죠.
그래서 높은 에너지일수록 이제 솔루션 슈레딩거 이퀘이션이면 솔루션이 진동을 프리퀀시가 더
커지는
커지고
거죠.
그러면
그렇죠.
그거에 요구하는 샘플링이 더 정밀하게 필요할 텐데 대충 n개의 솔루션이 나오는 게 딱 그 정밀도를 해치지 않는 선에서 나온다고 볼 수 있는 건가요?
그건 이제 프로블럼에 따라 틀린데 하이드로젠 아톰인 경우에는 나도 안 해봤어요. 하이드로젠 아톰을 왜 파이나이트 디퍼런스로 안 푸는지 내 생각에는 파이나이트 디퍼런스 메서드 처음 해보죠 여러분들 그죠? 왜 안 가르칠 것 같아요 물리과에서 파이나이트 디퍼런스 메서드.
되게 효율이 안 좋던데요. 지금 저희가 과제로 그러니까 다른 수업에서 과제로 지금 파이널 디퍼런스 메서드를 쓰긴 쓰거든요. 지금 윤방정식 풀 때 이제 이렇게 표현을 쓰는데 이게 지금 저희가 여기다가 이제 그 뭐지? 지금 라그랑지안을 풀어서 줄이는 걸 하니까 되게 계산 숫자가 과하게 많아지더라고요. 디멘전이 원 디멘전인데도 되게 높게 나와가지고 그래서 아까 얘기했던 대로 3디멘션 하이드로젠 그런 거 풀면은 되게 아웃 메모리도 진짜 그냥 계산이 과할 정도로 오래 걸리지 않을까 싶은데 손으로 푸는 것도.
과할 정도로 오래 걸리는 것도 사실이에요. 그러니까 3디멘션 안 풀고 대부분 일렉트로다이내믹스에서 2디멘셔널 프로블럼이에요. 3디멘셔널 프로블럼은 뭐 풀 수는 있지만 뭐 풀 수 있어요. 근데 많이 안 풀죠. 시간 속도도 많이 걸리고 뭐 그러는데 피직스 디파트먼트에서 안 푸는 문제는 내가 생각하기에는 이거는 개인적인 생각입니다. 내가 생각하기에는 피직스 디파트먼트 피지시스트들은 하이드로젠 아톰을 또 잘 못 풀어. 내 생각에 케미스트들이 훨씬 잘 풀어. 케미스트들이 대학원에서도 퀀텀 미케닉스 우리보다 훨씬 잘합니다. 잘하고 걔네들은 심지어는 아토믹에서 넘어서 몰레큘러 레벨까지 풀어요. 어프록시메이션을 통해서 물론 풀지. 근데 피지스트들은 하이드로젠을 딱 풀고 나서 그 다음부터는 힐륨도 잘 못 풀어. 거기 일렉트론이 2개 돌아다니면 어떻게 해야 될지 몰라. 하나 돌아다닐 때 핵이 하나 있고 얘가 올라가도 상관없잖아. 근데 힐륨 같은 경우는 2개 일렉트론인데 그라운드에 하나가 있고 나머지 하나가 왔다 돌아다니면 3바디 프로블럼이니까 못 풀어. 그리고 쓸데없이 렐러티비티하고 그 다음에 블랙홀하고 너무 쓸데없이 거기에다 신경을 많이 쓰고 있어서 그 다음에 파이나이트 디퍼런스 메서드는 언제 나왔을 것 같아요?
컴퓨터 나온 초기
다음에
예.
나왔죠, 그죠? 내 생각에는 한 90년대 파이나이트 디퍼런스 메서드가 이게 커머셜라이즈가 이게 우리가 지난번에 얘기했던 그 무슨 프로그램이죠? 그거가 나온 지가 한 20년 정도밖에 안 돼요. 2000년대, 1900년대 말밖에 안 돼. 그 전에는 다 그냥 개인적으로 풀었죠. 그리고 그 전에는 그냥 논문만 써내고 뭐 사람들이 푸는 사람 풀고 못 푸는 사람 그냥 못 풀고 그랬죠.
FDM이랑 메소드가 약속된 거지 사실 되게 비슷한 부분이 많지 않아요? 저희 옛날에 풀었던 FFT 과제 같은 경우도 거의 다 이거랑 거의 비슷한 접근을 한 걸로 알고 있어가지고.
그렇죠. 이거가 다가 아니에요. 아까 지난번에 얘기했던 것처럼 파이나이트 엘리먼트 메소드가 제일 파퓰러하다 그랬죠. 그게 샘플링 인터벌 마음대로 잡을 수 있으니까. 파이나이트 엘리먼트 메소드를 거의 다 푸는데 그 전 단계 이제 그 진화하기 전에 파이나이트 디퍼런스가 좀 더 간단해요. 그래서 파이나이트 엘리먼트 메소드보다 또 더 쓰일 때도 있고. 근데 그 전에 이제 이거를 샘플링을 통해서 문제를 푸는 방법은 수학자가 갤러킨이라는 사람이 나가 확실히 모르는데 이름으로 봤을 때는 러시아 사람 같죠. 갤러킨이니까 러시아 사람일 것 같아 내 생각에. 우크라이나 러시아 사람인데 그 사람이 최초로 했다 그래요. 갤러킨 메소드가 원조인데 뭐 그거는 이제 히스토리고 그건 이제 다 진화해서 지금은 파이나이트 디퍼런스하고 파이나이트 엘리먼트 두 메소드밖에 없죠. 뭐 다 이웃 사촌지간인데 뭐 거기서 거기긴 하죠. 근데 어쨌든 전자과나 아니면 기계과나 엔지니어링 디파트먼트에서는 심지어는 뉴턴 방정식을 풀려고도 엄청 노력을 많이 했죠. 지난 80년 동안 피직스에서 엔지니어링이 이제 스플리트 되면서 지난 한 70년, 80년 동안 그쪽에서는 엄청나게 많은 노력을 했는데 물리학자들은 블랙홀만 들여다보고서 아무 일도 안 하고 있어. 내가 보기엔. 그래서 파이나이트 디퍼런스 메소드를 아는 피직스 디파트먼트에 있는 사람 치고 파이나이트 디퍼런스 메소드를 아는 사람 별로 없어. 이렇게 쉬운데 테일러 익스펜션인데 그래서 가르칠 능력이 안 돼 내가 보기엔. 70년 동안 놀았으니 그게 되겠어. 그렇죠. 그래서 나도 피직스 디파트먼트에서 엔지니어링 과목을 들어보다 보니까 이거를 왜 안 했지 피직스에서? 그래서 대학원 때 엄청 쇼킹 받았던 기억이 납니다. 그렇죠. 그래서 지금은 멀티 디스플리너리라서 바이오 사이언스도 해야 되고 그 다음에 뭐 일렉트리컬 엔지니어링도 해야 되고 피직스도 물론 해야 되고 그렇습니다. 근데 사람들의 심리가 아직 시간이 남아. 사람들의 심리가 여러분들 그거 알아요?